In sections 6 through 11, we studied linear functions and the applications thereof. We looked at specifically linear functions in section 6. We talked about rates of change, which is an application of slope in section 7. Sections 8 and 9, we discussed the notion of a linear system, which uses either 2 or 3 linear equations at the same time. And then section 10 and 11 introduce matrices as a way to be able to solve a linear system with what we called Cramer's rule. So we've been doing a lot of discussion on linear equations and linear functions. Now it's time for us to switch gears and get into a new type of function called the quadratic function. And as it turns out, we have already studied some things that are similar to the quadratic function. We'll get to that in a moment. We have already studied the polynomial of degree 0 and also of degree 1. In section 13, we will officially define the word polynomial. So at this point, I just want to really point out where the degree 0 and the degree 1 come from. It says here that these are the constant function and the linear function, respectively. The constant function would be something like f of x equals 3. So there's no variable involved in the calculation, it's just 3, always. It's a constant value of 3 no matter what x value we try to plug in, because there's nowhere to actually plug in the x. Linear function would be something like this. F of x equals 3x plus 2. So that would be an equation of the form y equals mx plus b. So what makes these degree 0 and degree 1? Degree 1 for the linear function comes from the fact that the x has a power of just 1. On your constant, notice that you don't have really any variable there whatsoever. So technically, we can say that there is an x raised to the 0 power, because x raised to the 0 power is really just the same as saying 1, which is the same as 3. So we do get a constant function, and ideally we say that this is a degree 0 equation or a degree 0 type polynomial. So the quadratic function is going to be 1 degree higher than what we've already studied. Degree 0, degree 1, it's going to be degree 2. So definition 12.1 points that out. It says a quadratic function is a polynomial function of degree 2. So as I said earlier, we're going to focus on the polynomial definition in section 13. What I want you to take away from this is that a quadratic function is a degree 2 equation. We'll get more on the polynomials later. So just like with the linear function, there is a way to recognize a quadratic function by simply looking at its equation. This definition is going to give us the standard form, and that should say form, standard form of a quadratic function represented as an equation, and it's given by the following format. F of x equals a2x squared plus a1x plus a0. The a2, a1, and a0 are all represented by real numbers, provided that a2 is not allowed to be 0. The expectation is that you've been exposed to quadratic functions at some point previously before coming into this class. And it may not have been a very in-depth conversation about quadratic functions or quadratic equations, but some kind of exposure. And most often you'll see it written as the alternative form here, which is going to be with the ax squared plus bx plus c, where the a, b, and c have to represent real numbers, and then a is not allowed to be 0. So this will be the version of the equation that we're going to be looking at in this section. The first version is going to be the adaptation that we use when we talk about the more generalized polynomial definition in section 13. So we're going to see that come back again later. So for now, I want to go ahead and create a quadratic function, and you can do this as well. All you have to do is select 3 real numbers. I'm going to say let a equal, let's say 2, b can equal -3, and c can be equal to, let's say 4. So if I do that, then I can create the equation f of x equals 2x squared minus 3x plus 4. And just like that, you've created your first quadratic equation. And that can be used then to define a quadratic function. Let me try another version of this. I'm going to do something a little bit simpler. I'm going to say let a be 1, b equals 0, and then c also equals 0. And if I do that, then my equation looks like this. F of x equals 1x squared plus 0x plus 0. And the 0x plus 0 part really doesn't need to be there, since they're all just going to be 0 in value anyway. The coefficient of 1 on the x squared also doesn't really have to be shown. It's always implied, even if you don't write it. So really, this is the same as saying f of x equals x squared. And if you go back to section 2, where we created a bunch of parent functions, we created that whole library of parent functions, this is known as the squaring function. So really what we're talking about here with quadratic functions is that it is a more general form of the squaring function, which is good news because we know what the shape of the squaring function looks like, and actually as a consequence the quadratic function will also take on that same kind of shape. More on that to come. And I want to do one more example with you, because there's one thing about this definition for the quadratic function equation that we haven't really addressed. I talked about it briefly, but I didn't really address it fully, and that was the fact that a is not allowed to be 0. And I was always that kid that if you were told not to push the red button, I wanted to know what would happen when you push the red button. That's how I was when I was a kid. And so now I'm the same way. I want to know what happens if I let a be equal to 0. So let's say that I let a be 0, b is 3, and let's say c is 1/2. They're all real numbers, but we selected a to be 0. We know we're not supposed to do that, but I want to see what happens when we do. So then f of x is going to say 0x squared plus 3x plus 1/2. So anytime I have a multiplier of 0, that means the entire term is going to end up going away. So this is going to end up simplifying to just be 3x plus 1/2, which should look familiar. That's mx plus b. That's a linear function. So when we allow a to be 0, we no longer have a quadratic function, but rather a linear function. So it is absolutely critical that we have the statement a can't be 0, so that way it guarantees that we do have a degree 2 equation. Otherwise, it will reduce down to just being a degree 1 equation.